Now we are going in the more fancy stuff on getting the update rules for neurons on hidden layers. And as such, we will make use of what we call the delta rule. So the delta rule means that we are computing some kind of sigma JT, which is corresponding to, we can see this as some kind of local gradient. You know, it's maybe approximate as definition, but let's call this the local gradient of the neuron J for the data XT. So as such, you know, for the output layer, the delta GT is equivalent to that thing. So basically, the EGT, YGT times 1 minus YGT. This is again for using a sigmoid transfer function. And using this simplification, it's basically just to replace that element in the equation, give us that update rule for the output layer. And so this is for the weights connected to neurons from the previous hidden layer. And this is the update rule for the biases. It's the same thing that we just saw before, just that we replace this element by the delta GT. But this formulation is useful because we can use this to develop the update rule for hidden layers, just kind of redefining the delta here in a different way for making the corrections on the previous layers. So if we are looking at the error gradient for hidden layers, the developments are looking this way. So we have 3 then partial derivatives that we are developing for the hidden layers. So only this part is changing. This one is different from what we had before because this is really specific for hidden layers. These partial derivatives and that partial derivative are the same than before, so we will not redevelop them. This is what we have done for the output layer, but now we need to define the derivative of the squared error for sample t over yjt. So the error for a neuron on the hidden layer depends on the error of the k neurons on the next layer. So we talk about error backpropagation. So we need to look at the error coming from the next layer and how it is fed or it is used to correct the weights of the current neurons on the current layer. So let's go back to the definition of the squared error for this. So we have that thing. So this is basically the error of the neurons on the next layer. And if we develop the error according to YGT, we got into something like this. So we have this, we are computing the derivative of AKT, which is AKT squared. So basically we got something like summation over the case of EKT times the partial derivative of AKT according to YGT. So continuing this development, we've got into something like this. So we have that the partial derivative of for the current neuron J according to the following neurons on the neurons on the following layer, which is defined by the case here. So we see that that depends on the errors from the neurons on the next layer. So if we expand this as that thing, so we are still again are applying the chain rule. We got into this thing, we already have it. That one also up to some point. So yes, if we are considering simply here the developments for the hidden layer just before the output layer, this is what we have. So we say, okay, for the hidden layer just before the output layer, the AKT is equal to that thing here. So it's basically the difference between the desired output, RKT, versus the output of the neuron K on the output layer. And this thing is not different. We are still using the same thing than before. And then it gave us that thing. So it gave us that we have, so AKT is not changing. That thing here is giving us basically this thing. And we have here the WKJ is equivalent to the WKL for when L is equal to J, because for all the other cases, the value is 0. So this is corresponding to that, this is corresponding to that, and this is corresponding to that. So this is how we are making the development. And if we reshuffle things a little, if we define the delta, so we define that the delta KT for the output layer is that thing. This is what we defined just the slide before. Then we can simplify the rule with that thing. We can simply say that the partial derivative of the squared error here for sample T is, according to YGT, is equivalent to minus summation for all the neurons on the next layer, the delta KT, which is the sensitivity that we care, the local gradient that we care, times WKJ, which is linking, in fact, the current neuron with the next neuron. So each of these neurons on the which are on the next layer. So this is giving us a nice thing, and as such, then we can say that the correction of the corresponding error is that thing. Let's plug in all what we developed so far. We got this. So we've got basically that the partial derivative of the squared error over WJT GI for an hidden layer before the output layer is this thing. So it's minus summation over all the neurons of the next layer, delta KT WKJ times this thing, which is basic stuff coming from what we developed so far. And as such, what we can state, we can simply put that for that hidden layer, the delta GT is corresponding to this. So it's basically all this here. So it's all this stuff except the output WIT. So as such, we have something like the update rule for a weight of a hidden layer is equivalent to minus eta, the derivative of the error over WGI. So if we expand this for each sample, this is that thing. And if we expand this using that delta GT, we've got that rule for making an update on our weight. And the trick here is that, you know, we develop this according to the hidden layer just before the output layer. But by making this modeling of the delta GT, we are able to kind of define the updates for the hidden layers before the last. So like the hidden layers that are not directly connected to the output layer according to the same delta. And so we can just telescope, put inside the model this delta and use the deltas of the next layer as to update the current layer and define the deltas here to be used to update the weights of the layer before and so on. So this is through these deltas that we are defining the rule for back propagating the updates on the weights. And likewise, we define the update for the bias here. And so really the key is really to define this that way and reuse it for hidden layers others than the one before the output layer. And you can see here that in fact this delta is function of the next deltas, the deltas of the neurons on the next layer. So that's how we can do this, is basically to define the deltas according to the next ones, the ones on the next layer. So let's see this again. So basically we are looking at this delta because we want to update. We want to update that neuron. This is what we are looking for. So this update, the updates for that neuron depends on the deltas of the following neurons. Here we are looking at a neuron on the hidden layer just before the output layer. So these deltas on the right are the ones from the output layer. But the point is, with this delta, we are able to define the deltas on the hidden layers before. So they will reuse the same deltas and they will take that into account. And basically these deltas are the signal for updating the neurons that are back propagating, so propagating from the output through the input, through the network to updates the weights here, the weights that are characterizing, that are defining our models, our neurons, so our neural network.